All right, so let's take a look at the next section, which is section 2.4 on the complex numbers. So typically, complex number is the opposite term with respect to the real number. We also call complex number the imaginary number. Typically, the complex number will look like a plus bi. So I have two parts, real part and a complex part. Okay, so all right, so in this particular lecture, we're gonna talk about the imaginary unit I to write a complex number. So the key thing in a complex number field is I squared equal to -1. This is one of the most important, foundation for the complex numbers. In this particular section, we're going to talk about adding, subtracting, multiplying, and dividing the complex numbers. And we can also learn how to use a complex conjugate, right? The quotient of the two complex numbers. Complex conjugate. We get to all these detailed terms in a bit. We can also try to find the complex solutions of the quadratic equation. Okay, when there's no real solution, when there's no real solution. Okay, so let's move forward. So imaginary unit I, most important thing about I is it's imaginary number. So I squared is defined as -1. All right, so anytime you see I squared, it automatically becomes -1. Okay, keep that in mind. It's going to be very useful moving forward. So now we have learned some quadratic equations have no real solution. For example, like x squared plus 1 equals 0. If you look at it, there's no real solution because there's no real number such that after you square the number, it becomes -1. But once we learn the complex number, since we know I squared equal to -1, so now if you look at this, subtract 1 from both sides equation, okay, so we get x squared equal to -1. And since we know that I squared is equal to -1, so this is the same thing as saying x squared equal to I squared. Now basically, when you're taking the radical on the both sides of the equation, and then radical x squared on the right hand side, we get put plus minus I squared. So x equal to plus minus I. All right, so now as you can see, we get a couple complex solutions. Okay. From this, although there's no real solution, okay, no real solution, but we get a pair of complex solutions. Okay. So the standard form of the complex number typically look like a plus bi. Okay, and here we call a the real part. A is what we call the real part, a real number part. And bi is called a complex part. Okay. For instance, the standard form of the complex number -5 plus radical -9 equal to this. I'm going to show you how to do the conversion here. -5 plus radical -9. And since we know that I squared equal to -1, so right here we can simplify a little bit. Just rewrite it as 9 times -1. Okay, negative 9 equals 9 times negative 1. And now if you replace negative 1 with I squared, you'll be able to simplify this. Negative 5 plus minus negative 1 becomes I squared. Now if you simplify further, getting rid of the radicals, radical 9 becomes 3, radical I squared becomes I. So again, we get a pair of complex solutions. This is called a complex solution. Complex numbers, a pair of complex numbers. Okay. So this is very important term right here. I squared equals negative 1. Now help you simplify a lot of expressions in a complex form. Now definition of a complex number. So a typical complex number has two parts. A plus bi is what we call a complex number. And this is a standard form of a complex number. And then A is what we call the real part. A is the real part. And then bi, that's a complex part. Or you can also call that imaginary part. Similar term. And when the b is not equal to 0, we call this imaginary number. A plus bi is called an imaginary number. And a number of in the form of bi, meaning there's no real part or real part equal to 0, it's called a pure imaginary number. Just a couple terms for you to understand. So again, a typical complex number has two parts, real part and imaginary part. Okay. You can also look at every real number could be written as, let's say, a plus 0i. Okay, because 0i will become 0, so it's still going to be a real number. A is the same thing as a. Okay, so all the real numbers you could write it as a complex with a complex part. Okay. In terms of for two complex numbers to be equal to each other, like a plus bi, that's one complex number, c plus di, and that's another complex number. For them to equal to each other, a must be equal to c. So real part equal to real part, and then complex part equal to complex part. Also b equal to d. That means real part equal to each other. A real number equals. And then complex number equals. Our imaginary number also equals. Imaginary part equals. Now let's take a look at some typical operation with the complex numbers. So we know we have addition, subtraction, multiplication, division, subtraction, multiplication, the fourth one is a division. Now let's start with the addition. To add two complex numbers, you add a real part together and add a complex part together, and then write them separately. Okay. So for example, let's say we have a plus bi. Sum of those two, a plus bi plus c plus di. So you put a real part together, put into one parenthesis, and put a complex part together, put into the second parenthesis. And after that, you factor out the I, put it in the behind it. You get parenthesis b plus d parenthesis I. And the difference is very similar. you put a real part together. So maybe let me just simplify the difference right here. A plus bi minus c plus di. Similarly, first step, get rid of the parentheses. You can put imaginary 1 in the front, distribute it. So it's going to be a plus bi minus c minus di. And we put real part together. These two goes together. So we get a minus c. And we put complex part together. Plus bi minus di. So now factor out the I, putting behind the parentheses. So end up with b minus d I. Okay, just like the what's shown right here. Okay, and that's how you do it step by step. Okay, in terms of adding and subtracting complex numbers. So let's look at this particular example. Let's adding these two complex numbers. Step 1, get rid of the parentheses. Since it's the addition, so there's no sign concern here. So just simply get rid of it. So you're adding 1 minus 6i. Now we put a real part together. So 4 plus 1 goes together. And then the other one is 7i minus 6i goes together. So 4 plus 1 gives us 5. And right here, factor out the I, just like x. And it become 5 plus 1i. But typically, we just omit that 1. So it becomes 5 plus I. Okay. And that's how we simplify till the end of it. And similarly for the second one, get rid of the parentheses, so end up with 1 plus 2i plus 3 minus 2i. 1 plus 3 go together, becomes 4. 2i minus 2i, they offset each other, becomes 0. Becomes 0i, right? So eventually we end up with a 4 plus 0i if you want to, but you can just write it as 4, okay, as a real number. This one is part C deals with subtraction. So we just expand it first. We end up with 3i. Distribute it. 2 negative turn into positive, plus 2 minus plus becomes minus 3i. And distribute it again, minus 2 minus 5i. It's 3i minus 3i, they offset each other, right? Plus 2 minus 2 offset each other, and eventually end up with minus 5i. Okay. Okay. No real part. We call this pure imaginary number, right? This is what we call pure imaginary number. Okay. Now, part D deals with adding and subtracting. So again, first of all, get rid of the parentheses. So you have 3 plus 2i plus 4 minus I. And distribute the negative sign, both becomes negative. Minus 7 minus I. Okay, so typically we could put all the real number together. So 3 plus 4 minus 7 goes together. The other one is 2i minus I goes together. So it's going to be 7 minus 7 becomes 0 plus this is 2i minus 2i also becomes 0. So the answer will become 0. Okay, because these two cancel each other. They are exactly opposite. Okay. So the answer is 0. That's a real, right? This is a real number. 0 is a real number. Okay, many of the properties of real numbers are valid for complex numbers as well. Associative properties applies to the complex number operations. Commutative properties also apply. Distributive property also apply to the complex number operations. Yeah. Let's just look at this. Notice below we have a plus bi times c plus di. So now we deal with the multiplication of the complex numbers, right? This is multiplying two complex numbers. So keeping that in mind, I squared equals -1, right? You see why we need this all the time in a bit. So first of all, we FOIL this. A times c give us ac. And the second term is a times bi di. So it's adi. Okay. And then the third term is bi times c becomes bci. And then bi times di is bd. I times I becomes I squared. Okay. So most of the time you can treat I as x, except I squared equals -1. So when you have I squared, it automatically becomes -1. So right here, we see I squared here, right? That becomes -1. So this is AC. We can put complex number together, but let me simplify first. Plus BCI plus BD times -1. So plus minus become minus. So you get an AC plus minus become minus BD. That's a real part. Goes together. And then complex part goes together. ADI plus BCI. And now factor out the I, we get a job done. So AD plus BC, put I outside. All right, so we got it. So this is a simplified version of the when you multiply two complex numbers. So now let's use the distributive properties to simplify these complex numbers. So part A, 4 times -2 becomes -8, right? And 4 times 3i becomes 12i. Okay, so that's a simplified form. We cannot do anything about it, so leave as it is. Okay. And part B is multiplication of two complex numbers. So first step, we will FOIL this. So 2 times 4 becomes 8. And then the second term should be 2 times positive 3i. They both positive, so remain positive. 2 times 3 is 6i. And then the third term will be -i times 4 is -4i. And the last term is -i times positive 3i. Minus plus become minus 3i times I becomes I squared. Again, remember I squared becomes -1. So right here it's a plus 6i minus 4i, and that's 2i. It's like 6x minus 4x, it becomes 2x, very similar. And minus 3 times -1, that becomes real part. So a plus 2i plus 3. If you're adding a and 3, you get 11 plus 2i. And this is a real complex solution, complex answer, complex number. Okay, and that's how you're distributing using FOILing to simplify the product of two complex numbers. Now, very similar here, right? If you look at this, what do you notice about these two complex numbers? They look like they are, the sign in the middle are opposite, if you look at it. Okay, so one of them is 3 plus 2i, and the other one is 3 minus 2i. And then now pay attention to this, because a very interesting thing will happen here, and you'll see why this is critical. So 3 times 3 gives us 3 times 3 becomes 9. So 3 times 3, 9 first. Okay. And 3 times 2i, negative 2i becomes minus 6i. Now 2i times 3 is plus 6i. And then the last term is 2i times negative 2i plus minus minus. 2 times 2 is 4. I times I is I squared. And if you look at the middle two terms, they are exactly opposite. So they cancel each other. So minus 6i plus 6i. So the interesting thing here is eventually becomes a real number. So 9 plus, no, minus. Minus 4 times -1, because I squared equals -1, right? So 9 plus 4 gives us positive 13. As you can see, 13 is a real number. Okay. If you want, you can write it as 13 plus 0i. Right. Equally good. But again, 13 is a real number. So that being said, you can also look at this as a difference of two squares, right? You can look at it as a plus b times a minus b. So it just becomes a squared minus b squared. If you want to use a shortcut, and by doing this, we'll be able to get rid of the complex part here. So end up with the answer of the real number. So anytime if you want to turn the complex number into a real number, you multiply by the complex conjugate. So these two complex numbers are what we call the complex conjugates. Now let's look at the part E. Okay, so 3 plus 2i squared. So this is a perfect square, so you typically would just turn it into 3 plus 2i times 3 minus plus 2i. Okay, and again we've FOIL this. 3 times 3. 3 times 3 becomes 9, and 3 times plus 2i is positive 6i, and 2i times 3 becomes positive 6i, and 2i times 2i, both positive, becomes positive 4i squared. So now combine the middle two terms, right? It becomes 12i. Yeah. But because 6 plus 6 is 12. Okay, so now I squared automatically becomes -1. So 4 times -1 is -4. So this becomes 9 plus 12i minus 4. And 9 minus 4 becomes 5. 5 plus 12i. Okay. So you still end up with a complex number. So meaning a complex number square will still remain a complex number. Okay. Not like the previous one. Now let's talk about a complex conjugate. So typical complex conjugate look like this. These two are complex. A plus bi and a minus bi are typical complex conjugate. So for example, let me just give you a concrete example. If let's say we have 2 plus 3i, so the complex conjugate of 2 plus 3i should be 2 minus 3i. Because when you multiply those two complex conjugates, you end up with a real number. So the product of two complex conjugate becomes real number. Okay. So now let's take a look at some explanations on this. So pair of complex numbers in the form a plus bi, a minus bi is what we call a complex conjugate. The product of two complex conjugates will become a real number. Let's just verify that really quickly. Let's FOIL this. A times a becomes a squared. A times minus bi becomes minus abi. And then bi times a, both positive, becomes positive abi. And then bi times negative bi plus minus become minus b squared I squared. Okay. So now again, the middle two terms are exactly the opposite, so we cancel that. And then the remaining thing will be a squared minus b squared. I squared becomes -1. So now you end up with a squared plus b squared. Two negative turn into positive. B squared times 1 becomes b squared. As you can see, a squared plus b squared definitely is going to be a real number. That's why the product of two complex conjugates becomes a real number. Alright, so now let's learn how to simplify a quotient of two complex numbers and how to turn it into a simplified form without the complex part in the denominator. So we're going to use what we call a complex conjugate, right, to simplify this. So c plus di. So basically we multiply both top and bottom by the complex conjugate of the denominator, which becomes c minus di. Okay. And from previous example, we know that once you multiply by the complex conjugate, you just become c squared plus d squared on the bottom. You can also FOIL this step by step to get to the answer. Definitely there's nothing wrong with that. So now the bottom part becomes real number. So now we just have to FOIL the numerator and simplify. Okay, so a times c is ac. A times negative bi is minus adi. And then bi times c is plus bci. And then bi times negative di is minus bdi squared. So similarly, let's simplify ac minus adi plus bci minus bdi squared becomes negative 1 times negative 1. Over c squared plus d squared. Alright, so let's put a real part together. AC and BD should go together. AC plus BD, that's real part. And then I put a complex part together, so it's BCI, reverse order, minus ADI over c squared plus d squared. Alright, so now if you split up, you become you can separate into a real part and a complex part separately. So real part becomes AC plus BD over c squared plus d squared. That's real part. The complex part, once you factor out the I in the front, it's going to be BC minus AD dividing by c squared plus d squared. I goes outside. Yeah. Okay. So that's how we typically simplify the quotient of two complex numbers. And let's look at a concrete example. Actually, for the concrete example, it's actually a lot simpler. So now look at this. We're dividing 2 plus 3i by 4 minus 2i. So first of all, we multiply the complex conjugate to the denominator. The complex conjugate to the denominator is 4 plus 2i. Okay. So put this in the parentheses, put that in the parentheses. Now let's simplify. On the top, 2 times 4 is 8. 2 times 2i, that's 4i. And 3i times 4, 12i. And 3i times 2i becomes 6i squared. Okay. You can do slowly when you first start working on the complex numbers. On denominator, you can also FOIL this. So 4 times 4 is 16. 4 times 2i, that's positive ai. And then negative 2i times 4 minus ai. Okay. And then negative 2i times positive 2i becomes minus 4i squared. Okay. So now let's simplify. On the denominator, plus ai minus ai, they cancel each other. On the top, we get a plus 4i plus 12i is 16i. And I squared becomes negative 1. Okay. On the bottom is 16 minus 4 times negative 1. So right here it becomes a plus 16i minus 6 on top. On the bottom is 16 plus 4. That becomes 20. So a minus 6 becomes 2 plus 16i dividing by 20. If you want to split up into real part and complex part, so real part is 2 over 20, complex part is 16 over 20i. And now you can simplify, reduce it. Both 2 and 20 could be reduced by 2. So it turned out to be 1 over 10. Both 16 and 20 could be reduced by 4. 16 by 4 is 4. 20 by 4 is 5. Okay, there you go. That's a simplified solution for this quotient of the complex numbers. Now let's take a look at, for some quadratic equation, there's no real solution, right? If there's no real solution, then we do have a complex solutions. So now let's take a look at how we use a quadratic formula to come up with a complex solutions for quadratic equations. Okay, so now let's look at it. So similarly, we need to know this before we get started. Remember, previously we did we have a radical -3, since I squared equal to -1. So this should turn into radical 3 times radical 3 times -1, and radical 3 remains as it is. -1 becomes I squared. That's why we turn out to have the answer as radical 3i. Okay, and this is very crucial. So radical 3i is called a principal square root of -3. Okay. Also, it's called a root of -3. So typically, for any negative number, when you're taking the radical of negative number, you just become radical of that number times I. Okay, very simple. And this is very similar to the previous example. You just turn the expression as a times -1 and separate it as radical a times radical -1. We know -1 becomes I squared. Okay, so it's radical a times radical I squared, and it becomes radical a times I. All right, and that's how we get this simplified version, radical a times I. Okay, so now once we have this useful tools, then we could try to solve this. Again, this particular quadratic equation has no real solutions. You can go through regular channels, you won't find the real solutions. So the quadratic formula, that's what we're using to solve it. X equal to minus b plus minus radical b squared minus 4ac divided by 2a. So here a is 3, b is -2, c is 5. All we have to do, we just have to plug in all the numbers into the formula. So now let's see, we get a minus -2 because b is -2, plus minus -2 squared minus 4 times 3 times 5. Okay, and dividing by 2a 2 times 3, which is 6. All right, so let's move forward. So 2 negative 10 to be positive, plus minus -2 squared is 4, minus 4 times 3, 12, times 5, 60. Okay. Yeah, 12 times 5, 60, over 6. So right here, this is 2 plus minus radical of -56. Okay. Over 6. So we could simplify this a little bit. 2 plus minus, just like the previous one, it becomes 56 times -1. Okay, over 6. -1 is I squared, so it's 2 plus minus radical 56 times radical I squared over 6. Simplify further, it should be 2 plus minus radical 56 I over 6. Now 56 you can expand it as 4 times 14. So eventually radical 4 is 2. So radical 56 equal to radical 4 times radical 14. So this is 2 radical 14. So now you get a 2 plus minus 2 radical 14 I over 6. Now divide into that, you end up with the 1/3. 2 over 6 is 1/3 plus radical 14 over 3 plus minus I. So that's a complex solution for this quadratic equation. So when the quadratic equation has no real solution, then you have complex solutions. Okay. That's